casual conversations about science with the scientists themselves. It's the place to be to talk science. This is Coffee and Science with your host, Rob Parks.
Howdy, folks. Welcome to Coffee and Science. I see a lot of familiar faces in the chat, so I just want to make a quick shout out to Nerd Angle, Taddy. Thank you for showing up. Dora, great to see you as always. And Chris Durham, thank you again. Thank you for being here as well. So today, it is my distinguished pleasure to have on the show Dr. Clive Wells, Director of Study at Hughes Hall at University of Cambridge. So he is a mathematician, from my understanding. So howdy, Clive.
Hi, Rob. How are things?
Doing well. Just gearing up for this new semester.
Right. Yeah, good.
I start teaching on the 24th.
Okay, I think I start a little bit before you then. I've got a week to go, and then I start my teaching again. But before that, we've got to sort out what's called the winter pool, which is part of our admissions process.
Okay.
But yeah, that's the next big thing for next week.
Nice. Very nice. So tell us a little bit about. I'm very curious to know your educational background and what sort of research or what sort of what was your research focus or is your research focus? So we can start there.
I suppose probably start like most people going to university in the UK. I did A levels quite some time ago now, and I also did something called S levels. Now, the S levels no longer exist, but they were taken along with the A levels. The A in A level stands for advanced. So these are ones you do when you're 18, and you can take the S level paper, or at the time you can take the S level paper along with that. So I applied for various universities to study maths, and Cambridge was my first choice, and they gave me an offer. And so then I did my A levels, and I got the particular offer which they made me at the time. So then I arrived in Cambridge at Churchill College, which is my first choice college. So a little bit about Cambridge, perhaps before I go into too much detail about what went on. Cambridge is a collegiate university, so the university doesn't have a central campus as such. It has 31 different colleges, and there are also departments. So the organization of the university is that it is essentially the collection of colleges which has all the power. Okay. They've got together and then created departments to help with their teaching. So that's how historically how things have evolved. Now more power has actually gone to the center over time. But,
so you have the same, like you have the same departments in different colleges. Am I getting that right?
What's happened is that the departments have emerged over time. So you have the 31 different colleges. They would have in the past been, going back an awful long time, they would have been responsible entirely for the teaching of their students. But because the students have to take the same exam to get the qualifications, lectures have been done centrally, and this is and also research. So colleges have got together and produced and created departments. So the university has created departments to help with the teaching and the research. For instance, the maths department itself, I think it goes back only as far as sort of the 1950s. Although, of course, mathematics was taught in Cambridge for an awful lot longer than that. Yeah. Obviously, Newton, for instance, was one of our most famous mathematicians. So as I say, there are 31 colleges, and I've got a list of them here. There's Clare Hall, Churchill, Christ's, Corpus Christi, Keys, Darwin, Downing, Emmanuel, or Emma as we call it, that's Fitzwilliam, Girton, Homerton, Hughes Hall, Jesus, King's, Lucy Cavendish, Magdalen, Murray Edwards, Newnham, Pembroke, Peterhouse, Queen's, Robinson, Sydney, Sussex, Selwyn, St Catherine's, St John's, St Edmunds, Trinity Hall, and Wolfson. So you can apply to do maths in 28 of those 31 colleges as an undergraduate. Two of the colleges, Darwin and Clare Hall, only accept graduate students, and also for mathematics at least, Wolfson is also in that category. There are two colleges which are Hughes Hall, the one I'm at, and St Edmunds, who only accept students that are 21 or over. So
Okay.
we don't get as wide a choice of students as other colleges. It does mean we tend to get quite a lot of applicants from Singapore, for instance, because students there tend to be a little bit older because they had to do national service. So
Okay.
We get some very good students, actually, particularly from Singapore. Then there's two other colleges which are women-only colleges, and that's Newnham and Murray Edwards. So there's a bit of a mix of colleges, and some have good sort of inspiring architecture. Others have very modern amenities. So you can sort of pick which one you'd like to go at, or you'd like to go to.
Okay.
The way the admissions work, actually, I sort of mentioned this earlier. We interview our students. Okay, we've had to do it online this year and last year, which hasn't been great. Mathematics. Yeah. I think it's worked better in other subjects. But the idea is you apply to a particular college, they'll interview you and decide whether they want to. Well, first of all, there's a possibility if your grades really aren't up to standard, you won't be called for interview. Mm-hmm. If you are called to interview, we make some sort of assessment, and either you're really good and you deserve a place and we'll make you an offer, or you're really not up to the standard which could cope with the course, and so it would actually be rather unfair for us to make you an offer, because it's really no fun, even if you do get in, if you're really struggling with the course.
Yeah.
And then there's the people in the middle, and they're the ones we agonize over. And, they haven't done enough to be a definite offer, and they haven't done enough to be a definite rejection. So either we'll end up making some of them offers, or we'll put them in the pool. So the idea of the pool is that there may be people who apply to different colleges that are better than the students you're currently looking at, the ones who apply to your college. And the pool is a way for the colleges to look at all of the students that have applied, who have been put in the pool, as possibly be available to transfer between their application college and colleges that have spare space. So that process we're going through in the next week.
So they could potentially be rejected from one college, but picked up for another one.
Yes, the saying rejected is a bit harsh. It's just because some colleges will be oversubscribed. They'll have students they like and would take if they had the room, but they don't necessarily have the room. Accommodation is a big issue because pretty much all undergraduates in their first year will live in college accommodation. Most of them in their second and third years will be able to too, although it does depend on each individual college, what's actually how many rooms they have available for that sort of thing.
How many students does how many students does Cambridge have? Is it a large university in terms of population, or I'm assuming that that the enrollment or the population per college is different, but overall,
Yeah,
how many students do you typically
I
have?
think it's. I mean, I could probably look this up, but I think it's around about 18,000.
Okay.
So it's a good size, but that includes postgraduates as well as undergraduates.
Hmm.
Uh, we also, I mean, for mathematics, each year has about 250 students.
Wow.
So,
Okay.
yeah, so it is one of the bigger uh, universities for mathematics.
Okay.
So
Makes
what
sense.
happens is you have we call the course of study in any subject, an undergraduate course of study, a tripos. That's a strange word. What it means, what it actually comes from, is a three-legged stool that students used to be examined on when taking exams in medieval times. The word has stuck though, so we call the course of study and also the exam the tripos exam. And to get an undergraduate degree from Cambridge, you need to pass part 1 and a part 2. Now, part 1 usually lasts 2 years and is often subdivided into a part 1A and a part 1B. So in mathematics, that's how it works. I think in some of the art subjects, it may not be divided. So to pass a part 1, that usually you take an exam at the end of your second year. And then you go on to do part 2, which which is usually in the same subject. But in principle, it can be in an entirely different subject. So if you get a first class result in your part 1 and a first class result in your part 2, that gives you what's known as a double first. So that's a term which people have heard of, but not necessarily know the meaning of.
Mm.
So for mathematics, we have lectures 6 days a week, so including Saturdays, and typically they have 2 lectures a day, and that gives over an 8-week term. So the terms are actually quite short compared to many other universities, but we do have the lectures on Saturday as well as the other days of the week.
We do as well, although they're not there. It's full. We offer far fewer on Saturday
right.
than during the normal week.
Yeah, you see, all the lectures take place in the mornings, at least in mathematics.
Nice.
And what we have is a 24 lecture course or a 16 lecture course. So if you want to put that into 8 weeks, then the way the timetable works out is you'll have 3 lectures every week for the 8 weeks for the 24 lecture course. So sort of national holidays and everything, we ignore those, and we work Saturdays, or at least the students work Saturdays. I don't schedule any of my teaching for Saturdays. I think I deserve the weekend off.
Yeah, amen to that. So wait, So when you say that the students have basically 6 weeks worth of lectures, does that mean that they go for a particular course, they are in lecture once a day for 5-6 days, or is this just an amalgamation of their entire course schedule that semester?
So they typically have 2 lectures every day. So the first year's last term had a lecture on group theory and another one on probably vectors and matrices.
Okay.
And then so that might be Tuesday, Thursday, and Saturday. On Monday, Wednesday, and Friday, they would have something like, see if I can remember what courses they did. It was differential equations and numbers and sets were the 2 courses. So what happens is they get example sheets, which are problem sets given out by the lecturer in the lectures, or they're actually, these days, they're available online to download. And in addition to their going to the lectures, what they have to do is prepare answers to these things. And what we have is something called a supervision, which in other places we call a tutorial. So these are small group teaching where someone like me sits in front of them with two students, or maybe if they're odd numbers in the year group, that then I'll have a single student, and I'll go through and explain how to do the questions, or particularly the questions they got wrong, or if they have issues with anything from the lectures. So I spend a lot of my time doing that sort of thing. In fact, last term I think I did 10 different courses, supervisions. So they generally have 2 supervisions a week in addition to their lectures.
Are those mandatory?
Yes, they get into a lot of trouble with their director of studies, i.e. me, if they don't do the work.
Okay.
And actually, we have something called Part 3, which is for graduates, and that's open to people who have done degrees in other places. Now, they haven't always had this pressure to answer questions by a deadline and sort of have someone go through it with them. And that puts them at a severe disadvantage if they don't actually adopt that strategy, the sort of thing the Cambridge people have been doing their entire university career. So it's something I have to try and emphasize to students, that this is the way you have to do it if you want to get things to work. So yeah, we have lectures, then we have supervisions. The exams happen at the end of the year, and they have 4 exams, each of 3 hours long. In my day, we used to do it over 2 days. They have 6 hour exams on each day. I think then they don't allow that anymore. I think basically because you can, the individual students may have reasons why they need extra time, for instance.
Yeah.
And you just can't fit that sort of requirement in if you're doing it 6 hours over, or 6 hours a day for 2 days. It just wouldn't work. So they tend to be spread over the whole 4 days now.
Yeah, that's about what we do here.
Yeah, it's of a cross-sectional type. So it means that students can pick and choose which courses they take questions on, or at least that's how it is at the moment. There are proposals going around suggesting that our Part 2 might change to a modular system, but I'm not sure how much support that's got at the moment.
Okay.
So, okay, well, this sort of, okay, and in your college, you have a director of studies which organizes the supervision, so who will be supervising you as a student, and that's my current job. So getting back to history, I think I've set out how things are working within the university. When I became a student in my first year, so that was doing what we call Part 1A. After the first term, I had one supervision partner, and then I was repaired with a different supervision partner. And this guy was very good because he actually ended up coming top of the year. But what it meant is it really inspired me to know what was possible as a student in terms of answering questions for supervisions. You know, having someone who's that much better than you really can inspire you to know what is possible. Because I guess my first term, I was much better than my original supervision partner, and it was, you're judging yourself. He's the only person you can judge yourself against. So judging yourself against the best is a good thing. So I sat the 1A exams and did pretty well. I got a first, and just a few days ago, actually, I was tidying up and I found a list of my marks. I got 451 marks and 21 alphas. Now, an alpha is what each question is marked out of 20. And if you get more than 15 marks out of the 20, or 15 or uh, if you get at least 15 marks, then you get what's called an alpha. And so to get a first, you needed to have a certain number of alphas and a certain number of marks. So I exceeded what I needed by about 1.5 times, because the boundary was 300 marks and 13 alphas. So it is almost exactly 1.5 times, which I thought was a pretty good result.
Very nice.
In 1B, I did even better. And I know, well, at the time, that your director of studies wasn't really supposed to tell you where in the year you came, but can give you just a rough idea and tell you your exact results. So I had a different director of studies for my second year, and I got, and I know I came 12th out of the 250 or so students.
Very nice.
It was pretty good. I think I could have done even better because I didn't do the computational projects option, which is called CATAM, which is computer-aided teaching of applied mathematics, or at least that's what it used to be, and now it's computer-aided teaching of all mathematics.
Mm-hmm.
I think they decided they wanted to keep the acronym. So
no, CATS. I mean,
yeah, so we call it CATAM. Okay. Now, as part of my A levels, I've done computer science, so I was well able to do these computing projects. It's just that I didn't feel they were really mathematics, and I wanted to stick to mathematics. But the thing is, they were examined by submission of notebooks. So if you did them, they were marks already in the bank.
Okay.
So that's why I felt I could have done better. In part 2, I think I actually did. I did CATAM, and I think I actually came top of CATAM. But and I was also in the top 10 in that case. I didn't know exactly where, because I went back to the other director of studies. We didn't tell you your exact position.
What your exact rating was, yeah.
Yeah, but that, in a sense, by the time you're doing part 2, you're doing all sorts of different courses. The person who came top will be doing, I know, logic and set theory. You're doing general relativity. You're not going to get a fair comparison. So I got a first there, or actually what we call a first in mathematics for part 2 is called a wrangler. So I don't know if you're familiar with Terry Pratchett's Discworld. There's a character called the Senior Wrangler.
Okay.
And the term wrangler is what the mathematics department calls people who get a first. To become the senior wrangler is regarded as, or historically is regarded as, the greatest intellectual achievement attainable in Britain. That's a particular focus that's used. And there are many. If you look on Wikipedia, you'll see a load of a list of mathematicians and physicists, many of whom have gone on to do great things, and names you'd instantly recognise.
Okay.
So
nice.
Yeah. Then so that allowed me to graduate. Then I went on to do part 3 mathematics. Now, part 3 has a reputation of being the hardest course of its type in the world. So it's at the time it wasn't a master's course, although it was more difficult than any master's course around. So, but you only got something called the Certificate of Advanced Study in Mathematics. Later, they changed that to become a Master of Advanced Study or a Master of Mathematics. So that's what I did. So later on, I was offered to be able to take the degree and get the Master of Mathematics degree. So I did pretty well in that, and I was, and in order to do a PhD in the Cambridge Maths department, you really have to do very well in part 3. It's not absolutely an entrance requirement to do the PhD, but it's very rare that anyone will be admitted unless they have actually taken it and done very well.
Okay.
So I wanted to study general relativity and gravitation. So I went into so I applied to the general relativity group in the departments to become a PhD student there. It turned out that one of the people I'd gone to lectures with, one of the people who had given the lectures in part two, or in part three, was a guy called Gary Gibbons, who's pretty much a genius, and he was someone I wanted to work with, and I was able to become his PhD student that year. Gary Gibbons has worked extensively with Stephen Hawking, who was the head of the group.
Nice.
So I ended up working with him, and I also was asked if I'd like to be the department's nomination for an Isaac Newton studentship, which would have given me some extra money. Unfortunately, that studentship alternates between an award in optics and an award in gravity, and apparently it was optics' turn, so I didn't actually get the extra money associated with that studentship. But it did rather indicate to me that I must have done rather well in the exam to be the choice for the department to be put forward for this award. So I started working with Gary Gibbons, and one of the things you get with quantum gravity is an idea of the possibility of topology change. So what you can do in the quantum theory, you can look at the path integral formulation of the semi-classical approach to quantum gravity. And you can argue on heuristic terms that there's a quantum process associated with the creation of charged black holes by strong electromagnetic fields. So we usually talk about a magnetic field and a magnetically charged pair of magnetically charged black holes. The reason for this is that if you take an electric field, the sort of strength of electric field you'll be talking about would very rapidly cause electron-positron pair creation, and that would reduce the field. So you'd never get to the intensity needed to get this quantum process being a black hole pair creation being possible. So we usually do it with magnetically charged black holes. And what I was asked to do was see whether there was, or see if I could develop a uniqueness theorem for magnetically charged black holes in a magnetic flux tube as a solution of general relativity. It turned out to be a much more difficult problem than I think either my PhD supervisor or I realized at first. There's a rather technical reason for that associated with the properties of conformal maps or analytic maps in complex variable theory. But in the end, I made some progress towards that. But it really only took when I was writing up that I managed to get it to work. There were essentially two competing problems. One of which is I need to know the charge and mass of the black holes, but I needed to, and I can work them up by looking at the solution going off towards infinity, but only in a particular coordinate system. But I can only construct the coordinate system if I knew the mass of the mass and the charge of the black holes already. So it was sort of a catch-22 situation.
Okay.
Well, because there were these two problems which were sort of related, I'd only made partial progress. When I came to look at the situation a lot later, when I was writing up, I'd sort of forgotten exactly the details of my objection. And there'd always been a small voice at the back of my head saying I should try and use the Jacobi elliptic functions to solve this. And I was aware of them, but I hadn't really played around with them. So these are three functions called Sn, Cn, and Dn. They are approximations in some sense, or analogues, I should say, of the sine, cosine, and the number 1 in the ordinary trigonometric formulae.
Okay.
But it's sort of a more complicated version. Well, in the end, this nagging voice, I decided I couldn't put up with it anymore, and I'd silence it by just doing the calculation. When I did the calculation, I found out that the two problems magically cancelled off, and that they cancelled each other off.
Okay.
So I was able to push through the result in the end, but it was quite tough. Now, the other thing I was working on, or have been working on, was the idea of closed time-like curves, and so that these are time machines in the colloquial term. So there have been discussion about well, Stephen Hawking come up with this conjecture called the chronology protection conjecture, which suggested that if a closed time-like curve, so time-like means you can travel around it. An observer can with mass can travel around the loop, so it comes back into its own path. So that's why we call it a time machine.
Okay.
So I was looking at this with another student, and we made some suggestions. One thing was, Stephen also came up with the idea that unitarity can be lost in this process. Now, unitarity is the idea that, but we often talk about the S matrix being a unitary matrix, where the S matrix corresponds to scattering states from the far past moving to the far future. But in this context, it means just that the evolution operator was a unitary map. And so that meant that probabilities would be preserved. So all the probabilistic interpretation can be preserved. So probabilities will sum to 1 and they will be non-negative. Now, Stephen Hawking came up with the idea that actually what's important is a superscattering operator. The problem you get with just using the ordinary evolution operator is it maps what's known as pure states to pure states. And it seemed reasonable that you should, in this situation, allow for the possibility of a pure state go into a mixed state. And this means working with density matrices rather than ordinary quantum states. So we had a look at that, and we found that at least in the path integral formulation, there were problems. We would find that the probabilities you get would either not sum to 1 or would be negative. So it did seem as though the quantum field theory would break down in spacetimes containing CTCs, closed time-like curves, these time machines.
Okay.
We made some other suggestions as well on a previous paper as a way where we might restore the unitarity of the process. So that was quite nice. We got a nice email from one of the people who have been working in the field and whose paper we'd looked at. It made a slight error with the way he defined his quantum mechanical basis. He used fermions, and if you use fermions, you have to use computing operators. So that means you get lots of minus signs in places which you wouldn't for boson particles. It turned out we got a very nice email from this, and it later turned out that he won the Nobel Prize in 2004. So that was rather nice.
Nice.
He said although he didn't understand all our mathematics, he was really impressed with the paper. So We thought what a nice chap this David Proctor is. So that was really nice. In fact, there was another Nobel Prize winner that I came across when I was looking at the black hole uniqueness problem. I was able to go to the Netherlands, and what happened with Gary Gibbons had been invited to become visiting professor at the University of Utrecht for 3 months, and as his PhD student, I'd been with him for about 3 months there. It meant that I was able to go too. So that was really nice, and it certainly was quite eye-opening as far as how things were done differently there compared to Cambridge. So that was a nice thing. And so that was Gerard too. Or Toft. I think Dora will tell me how to pronounce his name. It's rather unusual. It starts with an apostrophe, which is always he's the only person I know whose surname starts with an apostrophe.
Yeah, I don't even. Okay, I mean, obviously, letter apostrophe is fairly common, but yeah, I don't know how I would. Okay.
Yeah. So yeah, I remember when we were visiting, we also went to Amsterdam for a conference. Journée Relativiste was the conference, which had been going in the Netherlands at the time. So unfortunately, I remember we were on the bus going back to the train station, where it was dropping people off all around the city, and we wanted to go to the train station. One of the other participants there had told us that, he'd point out when we were at the train station, and I think he forgot. So we ended up in the wrong place. And fortunately, Gerard Toft was there, and he offered to drive us all the way back to Utrecht and Zeist, which is where I was staying. So had a nice conversation with him about neutrinos, I think it was. I wanted to know whether he thought that neutrinos had mass or not, because it was still an unanswered question at the time.
Yeah.
So I remember him telling me that he thought the cosmological evidence was convincing to him that they did have mass, and of course that's what's turned out to be the case. So
exceedingly small mass, but yeah. Mass.
Yeah. I mean, you've got the neutrino oscillation experiments, which shows that they do have mass. So that's what I worked on for my PhD, and then I stayed around Cambridge. I took rather longer to do my PhD than is usual, because when you've got people like Stephen Hawking and you've got Gary Gibbons producing work of such quality from the group, that's the quality you sort of aspire to. And as
you tend to want to hang around that crowd.
Yeah. So it was a sort of very noticeable just what the quality of the research that's coming out of the research group was. So I did that. So I did that in order to support myself, because my grant ran out after 3 years. I'd done a lot of teaching for my college, Churchill, and I always enjoyed it, and I was asked if I'd like to continue as a senior member of the college, and so they were able to arrange it so that I could continue to do that sort of for another 3 years after I'd actually graduated. So I became a senior member there. But the problem was that, of course, I was spending all my time teaching, which meant that I wasn't doing the research, which is what gets you on in the academic world. But if you want to pay the bills, then you need to do the teaching, because I didn't have any other way of supporting myself.
Okay.
So when that finished, I went to Jesus, one of the other colleges, and I worked as I became director of studies there. I wasn't director of studies at Churchill. And then I also joined the computational modeling group of the chemical engineering department. I was reminded of the story about Richard Feynman, who instead of taking a sabbatical somewhere else in the world, he decided to go to a different department in his own university as doing something different. And that seemed
sure.
and I thought, well, yeah, I could do something different here. And so I went into the computational modeling group, and I was more interested in the mathematics behind the algorithm, the Monte Carlo algorithms they were using. And actually, some of the mathematics I ended up and papers I ended up writing were more mathematical than the papers I was writing in the maths department. So, convergence of stochastic processes and so on. Anyway, I enjoyed that, but it wasn't really what I was really interested in.
Okay.
So I eventually joined Hughes Hall about 6 years ago, and they appointed me as director of studies and also gave me a fellowship there. So that's really what's happened. And around about the same time as I joined, in fact, a little bit before, I started writing a book on asymptotic methods, which I'm still writing.
Okay.
And what happens, I wasn't entirely happy with the way the lecturer was explaining this material to the students. I thought, I'll write a short 80-page book which they can take away with them and just have the basics. And I thought that what had happened was that a friend of mine, who is director of studies in another college, had decided to write a book on dynamics and relativity, and I had been asked to basically proofread it and give my suggestions. And so I thought, well, if he can do it, so can I. So I just changed the LaTeX class from article to book, and it started looking quite book-like. So then I persisted with it. The problem I ran into was that I wanted to explain things carefully and in detail, and you can't do that in 80 pages.
Yeah, I was going to say.
Okay. Yeah, okay. I say 80, it'll probably end up as 120. I know what I'm like. And of course, now it's 500 pages.
Okay, so it kind of got away from you.
Yeah, but the thing is, I wanted to include all the proofs as a result, and I want to give all the explanations of how it all works. So that's how it has lasted this long. I can only really work on it during the summer anyway, because I'm teaching all the rest of the time. So yeah.
Seem to be the time to basically work on your own projects as opposed to all of the teaching responsibilities folks have.
Yeah, and actually, one of the things when I have been doing some research, because I can only really have the summer to myself, it's very difficult to keep up with the current research in any particular area. Mm-hmm. So one of the things I did write was a paper on adiabatic invariance. What had happened was that the senior tutor, who was also my fellow director of studies at Jesus, had been looking at had been asked by the faculty to have a look at the teaching of this particular course. So he went to lectures and noticed there was something he wasn't quite sure about in this particular area of mathematics, this adiabatic invariance. So he came to me because I teach this in supervisions, and he said he wasn't so sure about this particular proof that he was, and I said, was it the adiabatic invariance once? Because I knew it was the thing I wasn't entirely happy about, and he said yes, and then he suggested, well, perhaps we should work it out for ourselves, see if we can write a paper on it, and if not, then we would have learned something just for the process of doing it.
Sure.
So we had a go at that, and I think we ended up with a proof which was better than most of those out there and simpler. So I was pretty happy with that, and it's just a one-off thing.
Oh, very good. Very good.
And then there was another little project I did. You may know that in cosmology, the equations you get out of Newtonian cosmology are the same as those you get from relativistic cosmology. It seems a strange coincidence.
Yeah.
But I didn't necessarily believe in strange coincidences. I thought there must be a reason behind it. So I tried to find out what this was, and I wasn't really satisfied with any of the papers that were addressing this, because really they were addressing some parts of it, but not really explaining what was going on. So I worked it out, and there's a sort of hidden conformal symmetry, which means that if you take some parameter, if you set equal 1, you get the general relativity result. If you take the limit as this parameter goes off to infinity, it turns into the Newtonian result. And throughout, as you vary this parameter, the Einstein equations don't change. That means that the Einstein equations must apply to the Newtonian result as well. And so that's why you get the same equations from Newtonian cosmology as you do from general relativity.
Well, correct me if I'm wrong, but you don't get a cosmological constant in terms of Newtonian cosmology?
Well, if you put the I tend to put the cosmological constant, I just lump it into as dark energy.
Yeah.
So it's just part of the matter content. It's just convenient to do it in that sense. It's in some sense it's a matter of personal choice whether you're going to include that particular term as a cosmological constant or as dark energy. To keep this particular stuff simple, I'd include it as dark energy.
Okay. So what do you? I have not found a satisfactory explanation as to what dark energy actually is, other than some kind of negative pressure, basically just a pressure pushing outward. Do you have a better insight as to what dark energy actually is?
Well,
maybe.
Well, it goes back to what we were just saying. You can regard it as a cosmological constant.
Yeah.
If you do that, then you move it away from the idea of matter and a quantum field theory of matter, and so you might be in a better situation as far as the quantum mechanics goes. So, yeah, I don't know what dark energy is. You say it's a negative pressure. You can also think of that as a tension, in some sense. Obviously, cosmological constant doesn't have the right dimensions to be either a tension or a pressure, but you can sort of think of it in that way. So it's sort of the opposite of pressure. So that's still a bit of a mystery. But if you put it on the same side as Einstein did originally, then you don't have to worry quite so much about the quantum field theory. But whether that's the right thing to do, I don't know. Of course, the other thing is dark matter. Do you have any ideas what dark matter is?
I reject the macho explanation.
Right.
I don't believe that it is. I don't know if it's baryonic or not, but
right.
I would not be surprised if essentially neutrinos make up a bulk of the dark matter content.
Right. Yep. That certainly seems to be one possibility. I mean, my favorite possibility, and perhaps I like it because it will wind up the experimentalists, is that we live on a string theory is essentially correct, and we live on a brain. And we have a parallel brain, many parallel brains. Now, if you have mass on our brain, our universe, then because gravity can influence matter on the parallel branes because it can travel through the bulk of the system. It's not confined to the brain. Then you could get some sort of shadow galaxy or shadow matter forming or being attracted to that on the parallel brane, and that itself can give more gravitational attraction than would be justified by just looking at the matter on the brain, on our brain. So the great thing about this is that experimentalists will never be able to find the matter.
Yeah, I was just wondering whether you're saying that string theory is essentially correct. And the problem I have with string theory is essentially that there, as far as I'm aware of, there are no real there's nothing we can test to see whether or not it's actually viable.
It's very difficult to test string theory. I know that there's been a suggestion by Kalosh and Linde that in the very early universe, you may be able to see signs of the results of string-inspired inflation. But you need to look at the microwave background radiation at the moment. Things like the Planck satellite just aren't up to the job to look at the relative intensities of the scalar and tensor perturbations that you would expect from that. I mean,
what kind of scales do you need to dive into that?
Planck
is pretty sensitive.
It is, but I think it has to be a couple of order magnitude more sensitive to be able to attempt to answer questions like this. Okay. And of course, you know what's going to happen if what theorists are like. If you don't find that particular answer there, you just tweak the theory in some small way, and
of course.
Which is a sensible thing to do, actually. But that's what's likely to happen. But at least that provides one method where string theory could be put to the test.
Okay.
But we're not quite there yet. So what do you think about the James Webb Telescope? What are you looking forward to that potentially finding more?
Knock on wood. So I don't know, with James Webb, I'm trying to put this so it doesn't seem cruel. I almost want it to fail because the budget's been bloated, and it's when it comes to NASA, and not really making a coherent point here. It goes to where you're talking about with the Planck satellite, that there are a number of avenues of study that I think are getting ignored because of the whiz bang of James Webb. I think NASA has put too much of its priority into a single observatory as opposed to many smaller, more cost-effective observatories. But in terms of what James Webb can actually do scientifically, assuming that it actually all 344 failures actually don't happen, is exoplanets. I am a
right.
That's one of my points of interest in terms of astronomy is looking at finding these exoplanets, but also characterizing their atmospheres and looking for the biomarkers in terms of trying to find life. And so I'm hoping that James Webb will actually do as advertised and actually allow us to get detailed spectra of these exoplanets that we're going to find.
Yeah.
So, but I wanted to egress and ask about. So in obviously just kind of dumb it down a little bit. Obviously we've particularly with Raichi and FTFE and all that kind of good stuff in the flat Earth community.
Yeah.
There is this question of what exactly is gravity, and so I've been asking. It's something I've pondered myself, and I've asked colleagues of mine, can you give a more concise definition for what gravity is? Because we have this basically this what's the word I'm looking for, dichotomy, as it were, between classical, how we teach classical mechanics. We teach in terms of my intro courses. I typically do default and basically say that gravity is a force when I'm talking about
Yes.
Newton's law of gravitation, because it's far easier than to dump on these introductory students the idea of relativistic gravity. So, from your standpoint, what exactly is gravity?
Well, I was go straight to general relativity as my start. It's our best understanding of gravity that we have. So I just write down the Einstein field equation and say that is gravity, or those are the equations which describes the actions of gravity. Now, you would then want to, you may want to explain how that relates to the Newtonian worldview.
Mm-hmm.
So what we have with Newtonian theory is, well, Newton's laws only apply in inertial frames. And so we've got to start discussing what is an inertial frame before you can really get a grip on the relationship between general relativity, which has no preferred frames, no preferred coordinate system. And that's one of the great things about the theory.
Yeah.
Whereas Newtonian theory, you're really only supposed to do it in inertial frames. Now, of course, you can sort of get away with using rotating frames if you include the fictitious forces. And we do that, and we understand that mathematical transformation. And but what I would say is that transformation is entirely mathematical and has no physics involved in it. So I noticed that FTFE sometimes describes Coriolis and centrifugal forces in terms of conservation of momentum, but actually that's not really what's going on. Yeah. It's just a transformation which relates the acceleration in one frame to acceleration in the other frame. And you could change the laws of physics to whatever you like, and you'd still have this effect because of the transformation of frames. So it's essentially a mathematical result and not a physical result. Mm-hmm. Okay, well, we're getting back to how you get from general relativity to the Newtonian view. If you can find a set of coordinates where at large distances the space-time looks like the space-time of special relativity in a Cartesian coordinate system, that can be the basis of your Newtonian framework. So that'll be your inertial frame. Obviously, there are a set of them related by boosts, for instance. So we can, what you need to do is show that the other assumptions, which mean that you can look at the, you can expand the metric in terms of the time component of the metric can be written in terms of a function, which turns out, if you put the right factors in, to be the Newtonian potential at the end of the day. So the Einstein equations will turn out to give you Poisson's equation. Now, Poisson's equation is just del square phi equals 4 pi g rho, which is the equation which relates the gravitational potential to the matter content. And you find also that in this coordinate system, the acceleration is given by minus the gradient of phi. So what you've done is reproduce Newton's laws in this frame. And you would then say, okay, you've got an acceleration. If we just like we did with the rotating frames, we can regard that as a force in this frame, and apply Newton as you would. And that's what we teach at school level. And so, and that's what engineers will use. And it's perfectly acceptable. It's perfectly consistent with general relativity in the limits we're talking about, the ones where you have low speed and weak gravitational fields. So, yeah, there's no need to do general relativity in those situations, because if you try to do general relativity, your first approximation would be the Newtonian approximation anyway, and you rapidly do the Newtonian calculation. And then you realize you don't need anything more than that. There are ways of doing post-Newtonian calculations, but one would never do it for engineering applications, for instance. Inevitably, they'd have a 1/c² in the next term. So and c is very, very large. So you wouldn't get anything.
Essentially goes to zero.
Yeah. So yeah, I mean, that's perhaps a rather long way of saying what is gravity. But
okay.
Yeah, of course, you can then say, well, okay, we start with general relativity. Perhaps we should start with the results of a quantum theory of gravity. So then you say, okay, well, we can start, say, with string theory, and you've got the low energy limit of string theory gives a gravitational theory, which is very close to general relativity. It's not quite the same. There's an extra term involving the Kretschmer invariance, which is the RABCD term. But you'd expect that term to be small. It's second order in the curvature term. So essentially, you get general relativity out. So you preserve all of the results and all the successes of general relativity if you use this theory just as general relativity, because it has the correct limit, it has the Newtonian limit. It preserves all of the results of. It's consistent with all the results we've seen, which are consistent with Newtonian theory.
Maybe hopefully I'm following, but you're saying that string theory or general relativity is a special case of string theory?
No, it's a limit. It's when you can neglect the extra term in the equations, the quadratic term in the curvature. So it turns out to be important, for instance, when calculating the microstates of a black hole. If you have general relativity, then you'll get slightly the wrong answer. You have to. I think it was Robert Walters who came up with the correct way of doing the calculation for the string theory result. But if you want to get the right answer, then you don't just use general relativity. You use the string theory corrections. So
do you believe that string theory is going to be the ultimate bridge between quantum mechanics and gravity, or our current understanding of gravity?
I don't have any particular investment in either string theory or, say, loop quantum gravity or any other theory. String theory certainly has answered some questions, and in particular, the counting of the microstates of black holes is very encouraging. The fact that you can get the same answers from the classical theory, essentially, if you like, the black hole thermodynamics and the microscopic description. That I think came as a bit of a surprise, and a very pleasant surprise. So string theory, I think, has a lot going for it. It's an absolutely huge subject, and I don't tend to understand. I understand hardly any of it. But yeah, I mean, one of the things I like about it's compared to loop quantum gravity is it's closer. It seems to me closer to algebra. When we look at string theory, you've got a lot of analysis in there. You've got manifolds and so on. And I rather think that the idea of these interacting loops and looking at the algebra and the pure mathematics associated with those loops feels a bit more basic than assuming, say, a smooth manifold, which is what you do when you do string theory. To get that low energy gravitational limit, what you do is essentially assume a curved background and then see what's consistent with that curved background when you take the appropriate energies going the low energy limit. It seems to me that at least loop quantum gravity is trying to do something a little bit different. However, I think I still marginally prefer string theory because not only does it give you gravity, it gives you all the other particles as well.
Okay.
Although, of course, there are lots of questions about how we could possibly work out what particles does give us. It depends on the way the extra dimensions are compactified. And there's an awful lot of ways of doing that. And they'll give you different particle content. So it does give you the possibility of explaining all the particles of physics, not just gravity in isolation.
Okay.
But, you know, it's not as though we're in a position where we can actually deduce it directly from the theory because there are just too many possibilities. I think the number that typically is stated is something like 10 to 500 different possibilities.
Yeah, that's kind of a large number.
Yeah, it doesn't mean that it's wrong. It just means we're not going to be able to work through them very quickly.
Yeah.
Yeah.
So one of the things I found interesting about loop quantum gravity is the fact that it doesn't suggest that the universe, that time equals zero, as it were, is a singularity. That the universe was compressed to a very, very small volume, but it wasn't actually a singularity. I'm not familiar. What does string theory have to say about essentially what the universe looked like at time equals zero?
Well, I'm not very well up in it. I mean, there is one idea, which is the ekpyrotic universe,
Okay.
where you have two branes which collide, and essentially the energy of that collision goes into the creation of the universe. I mean, one thing I've been reading up on, just out of interest, within the last few days was the no boundary proposal. Now, this is essentially a paper from 1983 by Hartle and Hawking, and they suggested a way that the universe could come into existence just using the rules of quantum mechanics. So they take a Euclidean path integral approach to quantum gravity. So this will be a semi-classical approach. So you don't need to know what the particular details of quantum gravity are, and perhaps it's possible to get it out of string theory. And
Okay.
the idea then is that what you get is the tunneling from a solution which has no boundary. So there's no problem with boundary conditions into an expanding universe, and that seems to be the essentially the ground state for this quantum mechanical process. And I know a lot of people have done a lot of work on this. The particular solution that Hartle and Hawking looked at was for a K equals 1, and that is a closed universe. So the Euclideanized version is essentially a sphere, which is sort of cut off and then tunnels into a hyperboloid in higher dimensions, of course.
Yeah.
And it does seem that that explains an awful lot of the what could be going on. But of course, it is only a semi-classical approximation. It does seem to lead to inflation as the natural outcome of the quantum era. It does do away with the singularity because every point on the sphere looks like every other point on the sphere. So the laws of physics can apply just as easily at those points. It doesn't need anything prior or before. It always gets rather difficult to talk about these things because the English language isn't particularly well adapted to these ideas when you've got time being another dimension like space, you can't actually talk of words like before or something coming from something else. But those are more linguistic problems when you're trying to explain these things rather than mathematical or physical problems. So yeah, so I'm not entirely sure how the no boundary proposal does link in with string theory. It does, or at least Hawking claims that it also provides a solution to the arrow of time problem. So the fact that the entropy of the universe seems to have started in a particularly lower entropy state would explain why we experience an arrow of time. And I know that Hawking claims that claimed that this can come out of the no boundary proposal, and of course it's something that's certainly been worrying Roger Penrose. He's got the Weyl curvature hypothesis, which is that the Weyl curvature should be zero at the end, the beginning of the universe. His solution is a conformal cyclic cosmology, where you use conformal transformations to match the end of one epoch of the universe into the beginning of the other after all length scales have gone away, so you can do the conformal transformation safely.
Yes, some number of years ago, I actually had the privilege of listening to or hearing Penrose speak about this. This was back probably close to 20 years at this point. The man was still using overhead slides or transparencies to actually give us talk, which even at that point was a little bit outdated. But
well, I tend to use those as well, if I can.
Yeah, I guess that is when you're talking about teaching mathematics, it's probably a better way of doing it than with PowerPoints these days. But I have to admit that most of his talk, if not all of his talk, went over my head at that point. But I do remember the one quote was that the universe essentially gets so large that it forgets how big it is, and that's essentially the boundary, as it were, from an infinitely large universe to an infinitely small universe.
Yes, well, it's the idea of a conformal transformation. So in mathematics, a conformal transformation is one which preserves angles and the sense of an angle rather than individual lengths. There are some great pictures by Escher which illustrates some of this ideas. You've got, I think, one of the angels and demons and other things where you've got angles preserved, but the individual shapes are slightly distorted. So that's sort of the thing which Roger is sort of very much involved in terms of the in terms of black holes, for instance, in terms of working out conformal transformations. You've got these Carter-Penrose diagrams, which he and Brandon Carter invented. So conformal transformations and is what you use. The conformal part of the Riemann tensor is the Weyl tensor. So the vanishing of the Weyl tensor is a rather natural conclusion if you take all of this conformal cyclic cosmology seriously, and that is why in his model you get a low entropy state at the beginning of each epoch. So that's very interesting. I did have an interview with Roger Penrose when I considered which university I wanted to do my PhD in. I needed a backup just in case I didn't get there in Cambridge, and so I thought I'd go to Oxford and see what they were doing. In Oxford, you don't get PhDs; you get DPhils actually. But so I had an interview with Roger, and I remember it lasted 1.5 times the length it was supposed to, because I'd sent my Part 3 essay. So instead of doing basically 6 courses you could substitute one of them for an essay for one of them, which was basically a way of summarizing a set of papers and putting it into consistent notation and showing that you understood the material. I think my part of the essay was rather more detailed and had more equations than most. But basically, I went through and worked out every single equation in every single paper and basically reproduced it in my own language. And I decided just to send that off as a supporting, just in support of my application. I think that's what I said. And I remember that Roger had it there. He hadn't looked at it before the interview, but he kept referring it to as an MSc. And I thought, well, that's quite good, because an MSc takes a year to write your thesis. So he's saying it's as good as that. But of course, perhaps I should have pointed out to him that actually it was only 1/6 of the thing I needed to get the qualification for part 3. But yes, so I had a very, very pleasant conversation with Roger Penrose then. They did give me an offer to go to Oxford, but in the end, I think they knew that I was going to stay at Cambridge, so they gave it to me, but without funding. You see, if they'd given it me with funding and I don't go, then they've lost that funding. They can't give it to anyone else because it's too late. So now I advise my students. But by the time I know my results, which is probably June, that's too late for them to go and give it to anyone else. So effectively, they lose the funding.
That's strange. I would have thought they would have some sort of wait list where if the first candidate rejected it or refused or went somewhere else, then they would have a backup essentially to fill to put into that slot.
Yes, but I guess then someone would else. Then those people on the list would want to get. They're applying for other places as well.
Yeah,
and you got to bear in mind how that would work. But so I was offered a place, but I stayed at Cambridge. So.
Okay. Yeah, I appreciate the fact that your backup was Oxford of all places.
Yeah, well, it's good to support the smaller universities.
So
actually, Oxford are our great friends. Lots of people go between the two departments and the two universities. So yeah,
it's a friendly sort of rivalry, as
it is very much so.
Okay. I've often wondered what the actual relationship between Oxford and Cambridge was, in terms of how civil it was, shall we say. So I was wondering, so we have this kind of going back to the gravity.
Because we're an older college, so we have older students. So also sometimes students come here to study various subjects which are not necessarily, which historically have not been as rigorous as some other ones. So land economy always had the reputation of being something where people came to row. But I understand actually land economy is now a bit more rigorous. So yeah.
Yeah, you were saying before the stream that that Cambridge is getting larger, or is attempting to get larger.
Yeah. So a lot when you go to Cambridge, you go to the city centre, and that's where all the old colleges are and everything. But a lot of the departments have moved out of the city centre. So I think first in the 70s, probably the Cavendish Laboratory moved out to West Cambridge. And a lot of other departments have moved that way too, just because it's difficult to build new facilities in the middle of Cambridge. The maths department, I mentioned that I think this may have been before this. No, I think it was in the stream. Was created in about 1954 or something like that.
Yeah.
And it had buildings which were old Cambridge University Press buildings. The Pure Maths building in particular used to be a warehouse and was basically there's some sort of rabbit's warren of rooms built around the old warehouse, and that was next door to the Silver Street building. I sent you that Daily Motion video, which shows you the Applied Maths building, which is where I started doing my PhD. We moved to new buildings just before I finished, and that was and those new buildings well, they're absolutely fantastic, and the main building has grass on top, so I always think it'd be a nice Cambridge touch if I had a goat up there. Not a cow, because apparently you can't get a cow to walk downstairs, so you might be able to get it up there, but you won't be able to get it down. Yeah, so it's basically like the Teletubbies building. That's what it's been compared to. In fact, if you see the videos on my channel, if you look very closely at the thumbnails, that is actually the maths building. It's done at night though, so you can't see too much of it, but that is the new maths building.
So what was the motivation for putting grass on the top of the building?
I don't know. I think it's probably ecological reasons, or it's what the architect decided. It's a nice touch. You can go up there and have a nice view of Cambridge. You can look at you can see King's College Chapel, which and the University Library. I think there's a regulation in Cambridge that nothing should be taller than King's College Chapel these days. So the skyline is pretty uninhibited by various other large buildings.
Nice. Yeah. I don't know. I think putting a grass field on the top of a building would invite someone to start driving golf balls off the top of it.
Well, I don't think it's happened yet. I suppose you'd have to get you'd have to get up there. I mean, we don't have a huge amount of security, I guess. Although we have swipe cards at entry, I suppose, so it wouldn't be that easy to get there. And I suppose there's security cameras around. But no, I don't think anyone's actually tried that.
Tried it yet?
Yeah. There have been all sorts of stories in the past about students doing all sorts of strange things. We get our degrees in what's known as the Senate House, which used to be the old University Library at one stage a long time ago. And there's a story that the students, one time, I think it probably would have been the 1920s or so, managed to get a car onto the roof of that building. So I guess cars in that time were a little bit easier to manhandle. But you're not supposed to climb all over the buildings. You'll get into trouble for doing that.
So, kind of going along the topic of academia, just what do you think is the largest challenge that say Cambridge is facing in terms of moving forward, in terms of growth, as it were?
Well, I think part of the problem is the colleges want to expand, but we have limited capability in terms of buildings and lecture theatres and that sort of thing. So that is a bit of a problem. There has been talk about, or from time to time, there's talk about having a new college in Cambridge. At the moment, I think that idea seems to have disappeared. But just expanding, I guess. One of the other problems, I guess, is online provision. We don't have a huge amount of online courses which are available to the general public or anything. Over the past few years with COVID, you have had lectures being recorded for students, and we have various systems for that. But I'm not quite sure that's quite what we really want to do. It was pointed out that going to lectures is good discipline. You know, if you have to get up in the morning and actually go to a lecture in order to get the lecture notes, that is imposes some discipline on your and regularity on your day. Whereas if you can say, oh well, I'm going to sleep until 2 a.m. Or 2 p.m. and just look at the video of the lecture later, that's not going to be an effective way to study. So I think we need to work out what's the best way to adopt a new technology and make sure that whatever we use is effective. So I think that's one of the big challenges.
There is in the States, there is this burgeoning sort of discussion in terms of the quality of online education. Prior to COVID, this was some when I was at LSU, or Louisiana State University. There was this grand notion of actually essentially doubling the size of the university in terms of enrollment by offering a large number of online courses. Cynically, we thought that was basically just a cash grab. That we're just trying to enroll as many students as possible in order to get as much funding for the university as possible. But I question whether or not that's a good idea, because particularly with COVID, as you were saying, there is a certain lack of discipline in terms of instead of making yourself reasonably presentable, going to a lecture, sitting through the lecture, and engaging with your fellow students, and also with the professor. I've noticed with my particular online classes, they're so easily distracted by whatever else is on the internet that when I do actually get to see their faces, I can note that they are not really paying attention to what I have to say, and they're obviously searching the web or what have you. I actually had one student who was apparently delivering food while he was in my class. He was one of these Door Dashers or whatever. So, what do you think? Do you put any stock in online teaching moving forward?
Well, I think for some students it can be a good thing, and for other students it can be a bad thing. So I think you could make a case for it, but I'm a bit reluctant to put too much online. I think, as I say, the discipline of having to go to those lectures to get the notes is very important, and it's something I don't think you would learn, or I don't think I would have learned quite as much as I did if I had just to put on a lecture and do it that way. I mean, one of the things I used to do was go to lecture and I'd deliberately take very scruffy notes. The reason for that is that then I would force myself to write them out neatly during the afternoon.
Okay.
And not only do and as I go through them, I can check all the equations, make sure I understand everything, and do that. Now it would, okay, you've got 2 or 3 hours of lectures in the morning. It's going to take you 3 hours, 4 hours in the afternoon just writing out your lecture notes, and then you've got all your supervision work to do. So it's very time consuming to do it that way. Now, if you had online notes, I'm not sure or if you've got an online course, I'm not sure you'll do that. And so I'm not sure that you'd learn the material as thoroughly.
Okay.
But there'll always be the assumption, well, I can always look at that later, or I can always go back and look at it. And
you never
those good intentions rarely ever come true. So, I mean, the other thing I have noticed about students is that, perhaps it's just math students, is they have a reluctance to go and use the library. If they don't understand, if I didn't understand something in lectures, what I would do is, after working at it as hard as I can, I'll go to the library and see if I can find a book which explains it.
Mhm.
It seems that students never do that these days. Some of them will, the good ones will actually Google something, and actually the Wikipedia pages in mathematics are generally very good. And actually that's what I do. I find something which I'm not quite clear about. But it's surprising how many students will say, "Oh well, I'll not do that. I'll go to supervision and I'll get Clive to explain it to me," which is not really what they should be doing. Because I think a lot of essentially you learn by trying to do the questions. If
Yes.
I've often had the case where students will come to me and said, "I understand the lectures, but I can't do the questions," which immediately says to me that they don't understand the lectures.
Exactly.
So you really don't learn as much from seeing someone else do a question as trying it for yourself. When you do it for yourself, you find out the dead ends. You see why something works and why something doesn't work, and you lose 90% of the benefit of a question if you see someone else do it rather than having a go at it for yourself. And so waiting to get someone to explain it to you rather than going to the library, I think, or looking or trying to get some clue online, I think is detrimental.
Yes.
So yeah.
I've
But
definitely
perhaps
have. Mhm. Go ahead.
yeah. So perhaps is it in that sense, online is good as a surrogate library.
Yeah, I had my postdoc, basically boss or advisor, whatever, how you ever want to phrase that.
Yeah.
He was basically anti-book in the sense that he was like, at this point, if I want to know something, I just go on the internet. He actually thought that books were essentially an obsolete form of learning, which I found to be an interesting perspective. So but I do
Yeah.
agree that if with particularly in particularly in physics and presumably in mathematics, in order to really understand something, you have to do it. You have to be active in your learning experience, as you said,
Absolutely.
in order to basically find the pitfalls and work through those. And really, that's the best way to actually understand a subject is by, as you say, by doing it.
Yes. Yeah.
Because you can sit and lecture and you can absorb the information. You can tell yourself that this all makes sense and actually it works, but without actually working problems that probe different aspects of what you're learning in class, I don't think you truly appreciate the implications of what is being taught.
Yeah. I always tell my students when they're okay, they've just had their Christmas vacation. Um,
Mhm.
it's really important that they revise over the Christmas vacation and also the Easter vacation, because there is not enough time for them to learn the courses. So typical questions in the exam will have a bookwork component. So they'll have to reproduce the proof of a particular theorem. So state and prove the mean value theorem or something like that, and then they'll
Mhm.
have an application to it. So what I really try and impress on them is that they will have to learn the contents of their entire lecture course. Now that doesn't mean learn the thing verbatim, because the way to learn mathematics is to learn the little tricks of each individual proof, and
Okay.
then you can sort of go between one step to the other. It's pretty obvious what to do, but you learn the key to each proof, and so I tell them to go through their notes. You can do about 10 pages a day. Just try and read then close your notes. Try and write out the theorem that you're learning, if it's a theorem, or the piece of mathematics if it's something more on the applied mathematics side. And they go through that that process for all of their courses and all of their notes, and they're not supposed to do too much in a day, because if they do too much in a day, they'll have forgotten half of it the next day.
Yeah.
But
I
at the
think you
same
reach a
time,
point of diminishing returns. The longer you study, the more your brain sort of checks out, and you don't really retain that information.
which is why you have to start your revisions so early.
Yeah.
And the other thing is not that doesn't take all of your time during the day. But what you've got is you've got all these other questions from these example sheets. So the way we usually work it is that there are 4 example sheets for a 24 lecture course. So that means, because the course starts fairly slowly, you can't have an example sheet on very early during the term, because the students haven't done enough of the course in order to make that worthwhile. What I usually do is have 3 supervisions on the course during the term, and then the last one is left over to the beginning of the next term. So there are these 4th example sheets around, which the students will have to do over Christmas, and so they get a mixture both of their notes and the example sheets, and later on, if we're talking about Easter term, they'll have past papers to do as well. So that's how I encourage students to learn.
Do you find that to be? Do you find that your students are actually receptive to that sort of strategy?
Yes, actually, I do. The thing is, you've got to get them into good habits when they first arrive in Cambridge.
Okay.
For instance, copying out your notes. If they get into the habit of not doing that and just have scruffy notes, or notes that they took in lectures and never look at, or never go through in detail, then that will put them at a disadvantage, and it's very difficult to break out of bad habits. Now, because I'm a director of studies and I see my students when they first arrive in their first year as well as their second and third year, I can really drill into those that make sure they have good habits right from the very outset. Yeah.
How many students do you typically oversee or have
well,
go through the program?
Yeah, at the moment we have Shoehold doesn't have a large number of mathematicians. It's got a lot of graduate students, but not so many undergraduate students. We have 2 students only in the first year. We have 6 in the second year. We have 2 in the third year. And then I think we've got about 14 doing part 3. So part 3 is slightly different, because these students have actually come from other places and don't come through the undergraduate admissions route, so that they will tend to get assigned a college, and they can be from all over the world. So I try to give them exactly the same advice, but it's often a bit more difficult to get them to get into the habits which work in Cambridge for this course, if they've been successful in other places. And all of these people have been the top 1 or 2 in their universities before, so they would be reluctant to change their working habits if they worked well in their previous institutions. But if they don't, then there's a good chance that they won't do as well as perhaps they could do.
They might get overwhelmed by what they're overwhelmed by the course material.
There are something like 80 different courses that they can take in maths and physics in part 3, and it is incredibly intense. And you know, it is, as I said before, it's one of the hardest courses of its type in the world. So and it starts at a very fast pace, actually, as does all of the courses in the Tribos. But particularly, you see what part 3 is. It's called part 3 because it is a continuation of the part 2. So it's really designed originally for Cambridge students, and it's only fairly recently that students from outside have been allowed to take it as a 1-year master's course. Now, of course, that means that those coming in from outside won't have exactly the same background in courses, so it's automatically rather more difficult for them because you may have a great background, but if it doesn't quite match up with the courses, you still might have gaps. So it's already quite a tough thing, and the people going on to do part 3 have either got a first at Cambridge or they've got a very high 2-1. So they're our best students, in fact, that continue, and it can be rather overwhelming for students that have sailed through their previous institutions.
So this is a question that was Taddy. I don't know if Taddy's still in the watching, but how many students on average egress from class during the duration of the course? Essentially, given the rigorous nature of Cambridge and the classes, do you have a feel of what the actual turnover rate is?
We generally don't get people dropping out. It's usually we try and do everything we can. One thing we can do if the student fails their exams, but we don't have a resits or anything like that, but there is the possibility of intermitting and if their supervision reports, because supervisors are required to write reports on their students at the end of the term. If their supervision reports are good and they have the support of their college, they may be able to progress to the next year. Sometimes they don't if they've been lazy, then they would have to leave Cambridge. We don't have a very high dropout rate at all.
Really?
Mainly our students are some of the best in the world. That's the students we attract. And most of them realize that that they want to be here. So, and if they want to be here, that they have to work. And also because I guess we take, well, at least at Hughes Hall, because I do so much supervising, I'm seeing my students, the ones I'm responsible for, every week. So they don't really get the opportunity to slack off. We try everything we can to make sure that not too many students egress the course prematurely.
That is something that is fairly foreign to the experience over in the States. Unless you're working with a particular professor on a research project, you really don't have. I mean, technically speaking, we have academic advisors who are supposed to watch out for the students' best interests. But I think either given the number of students they have to mentor, or the fact that it's not really a requirement in any way that you go talk to your advisor, a lot of students over in our larger universities tend to get overlooked, and there tends to be a fairly significant attrition rate.
Right.
The large universities that I've worked at.
I mean, the other thing we have is that as students not only have a director of studies, they have someone called a tutor. Now, a tutor doesn't do any teaching, but they are responsible more for the pastoral side of things. So they'll deal with the interactions that the student has with the university if they want to make an appeal against their exam results, or they have they need to intermit, or they need a form signed or something. Then they have a tutor to go to in rather than their director of studies. What this means is that they can actually divide their life into an academic side and a personal side. And the way the university deals with, say, the personal problems, that will be something which they may talk to their tutor about, but they don't have to talk to their director of studies on the academic side about it. So they can divide their two lives into two parts, and hopefully, if something's going bad in one part of their life, it doesn't affect the other part.
So the university helps facilitate sort of the compartmentalization of keeping a work-life balance, as it were.
Yeah, although there isn't too much of that, to be honest. Uh, we work our students very hard.
Yeah.
If you want to be, if you want to get a first, that, or a distinction in part three, that other people are competing for that honor, and they're not going to let up. So you're better not let up. And so everyone drives everyone else on to higher and higher things. So people work incredibly long hours. Of course, it all depends how smart you are, really. If you're clever, maybe you don't have to work quite so hard. Of course, what you also get is people who are clever and work hard.
Yeah.
And then there's no real catching them.
That's very, very true. Those are the people I get most impressed with. Is not only do they have brains the size of the planets, but they have that passion for the subject that they want to envelop or invest. They want to basically envelop themselves within their field of study. And so those are the people that I most envy when I encounter them.
Yes.
I have a question for you from Carl Edwards. What is the hardest thing to learn into being a good student?
Sorry, what was the hardest thing to learn to what?
I guess what is the hardest lesson that a student has to learn in order to become a good student? Do you think?
I don't know. I think it must be a certain amount of discipline in order to actually get down and actually learn the stuff. If you're not doing that, then that's going to be a problem. I certainly remember for our admission process, we have an step, the 6-term examination papers. And so these are taken along the same time as the A level. They're, in a sense, the successor to the S level that I mentioned right at the beginning of the stream. Except these are specifically organized by Cambridge, or in fact are it's the Oxford and Cambridge Examination Board, or whatever it's more. So it's Cambridge Assessment now. I think other people who run it, which is sort of connected to the university but not part of the university. It's sort of a separate legal entity or something. So the grades you can get for that are S for scholarship, 1, 2, 3, and U. And in the past, we've sometimes got people with S and S. So there are now only 2 exams. They're called Step 2 and Step 3. There was a Step 1, but that's been discontinued. And most of our offers require people to get a 1 and a 1 at Step, in which accounts for the mathematics A level and the further mathematics A level. So we do some. In the past, I have known students that have come in with these 2 S's, but got nowhere in the first year of their exams, and look like they're going to fail. I remember one particular individual when I was at Jesus. I won't mention his name. I think I've forgotten his name anyway. He had these 2 S's, and we thought, oh, well, that's really encouraging. But he seemed to learn nothing, and perhaps he was lazy, or perhaps he just reached his intellectual limit in getting those steps. With him, what we were able to do was try and persuade him gently to go off and study another subjects, and we were going to change to computer science. I had a chat with him, and he said, and suggested this to him, and he said that he had been thinking about changing to computer science for his 3rd year rather than his 2nd year. But the director of studies in computer science was very happy about this, because she found she had someone who had 2 S's at Step. Now, I actually think I think what happened is he did actually survive and get past that year, but I think he got the lowest pass as well. I'm not sure what happened. But
Yeah.
that's one thing that we can do. We can move people into other subjects if they're doing really badly and we think they're going to fail if they continue. It's possible to transfer into maths, but nobody ever does. It's always the other way around.
So you have people leaving the program or switching
Yeah.
out of the program rather than switching in.
Yeah. One of the things which you can do is apply for maths with physics. Now, there's really no point in applying for maths with physics to Cambridge. I'm not sure I should say that publicly, but as it is a legitimate option. The point is there is so much theoretical physics in the maths department. We like to say it's because Newton was there. Of course, Newton wasn't really in the maths department because the maths department didn't exist until the 1950s, but he was at least in the university as a mathematician. So we do have a rather large component in the department, which is perhaps theoretical physics or applied mathematics. So it's not usually worthwhile people going to do the maths and physics, because if they do the maths and physics, that means they have to do experiments at the Cavendish labs, and all the students hate doing the experimental stuff. Well, they've applied to a maths department, so they're clearly more interested in the theoretical physics side, rather than experimental physics. So it's not so surprising. And then they end up doing a couple of courses, and I think one of them is the relativity course. They do that in the physics department rather than the maths department. But I don't think that's quite such a good course, because as mathematicians, you can assume a certain amount of mathematical sophistication, and you can introduce things like 4 vectors and so on in your first year course. Very useful for when you study relativistic electrodynamics or general relativity in later years. But if you've gone to a physics course, they just tend to try and do it without all of the mathematical sophistication. And what they end up doing is just putting gamma factors all over the place. And unless you know where they come from, then it's very difficult to know what's going on. So
do you think that the students are doing this because it's easier? Less rigorous, as it were?
It's because they'll apply for maths with physics because they don't understand how much physics there is in the mathematics course. And they're generally interested in the theoretical physics. And if they apply to other universities in the UK, if they go and do maths, they will just be doing analysis and algebra and things like that, the sort of thing, number theory, probability, or whatever. But they wouldn't necessarily be doing quite so much theoretical physics. So they put the maths with physics option without realizing that there is so much theoretical physics in the maths course that they would be better off doing the maths course, the straight maths course. But what it does mean is that we can sort of push people off who are going to fail, or we think are going to fail, into the physics course if they didn't do very well in their first year maths exam, because it sort of stated that in the admissions stuff that you can always transfer to physics. But we also have people going to more unusual subjects. I think the senior tutor of my college, or rather the one who's just retired, he started off as a mathematician and very quickly changed to theology. So
interesting.
It's always possible. And as I say, as I mentioned earlier, you have to do a part 1 and a part 2, and they don't necessarily have to be in the same subject. So it is also a natural place where you could change, although whether you'd have the background to do a part 2 if you've not done a part 1 in the same subject is another matter.
Yeah, I was noting that there seemed to be a lot of overlap in terms of, or a fuzzy line between physics and mathematics when you're talking about what you do in your sort of fields of expertise. And I'm used to the sort of the other side of that, in
Yes.
terms of astronomy and physics. And physicists like to derisively say that astronomy is essentially not a science in and upon itself. It's just simply applied physics. And I have to say that they do have a certain point to that. And I do encourage with my students when they come to me and ask me, or first years or second years, and they're asking me whether or not they should, what should their emphasis be in the undergraduate level. I tend to point them towards either if they are so inclined to double major in physics and mathematics, or physics and computer science, if they really want a if they really want astronomy as their profession, because that allows them a good framework from which grad student, or you can learn astronomy or the specifics of astronomy in grad school, and but you need that heavy underpinnings of physics and mathematics to really understand the nuances of what the astronomy is trying to say.
Yeah, I think one thing that you find out when you do a PhD is your research becomes very focused indeed, and it's very difficult to get sort of to learn sort of an area of mathematics or an area of physics when you're just really concentrating on such a fine area yourself. You just learn what you need to in order to get to the results that you need.
Yeah.
And that is something I have found. So what I've also noticed is that because we have so many colleges, we often have dinners at different colleges. So as a supervisor, you'd be invited at the end of the year or sometime during the year to a big formal dinner at various of the other colleges. And sometimes I'm talking to physicists, theoretical physicists who are in sort of the Cavendish department, or the physics department. And very often they say to me that they wish they'd studied mathematics rather than physics as an undergraduate degree, because they find they have to catch up on so much mathematics in their theoretical physics.
Yeah.
And I think Stephen Hawking himself mentioned something like that because he did a physics degree at Oxford, and he said that mathematics was rather unchallenging. But of course, when he came to Cambridge and had to do his PhD, he found he had to learn an awful lot of mathematics because that's just the way theoretical physics is. It is essentially doing maths.
Applied mathematics, yeah.
Exactly.
Okay. Well, moving a little bit away from academia, what I wanted to talk to you before this stream gets too long is, so what I'm curious about is, obviously you and I are sort of active in the flat Earth debunking sort of community, at least in the periphery of it. Do you feel that there is either in the UK or globally or what have you, there is a large science denialism sort of, is science denialism a large factor in our society, or is it a growing factor in our society, or do we live in basically an echo chamber on YouTube when it comes to dealing with flat earthers or creationists or what have
I
you?
think there is an element of that, yes. I don't see a very large anti-science. Obviously, when you're at university, you don't really come across anti-science people or so on. So you're really talking about my impression of what's going on in society in general. Now, it is true that a lot of our politicians are untrained in science and often have degrees in art subjects. It is, I think that's regrettable, but I guess if you want to become a politician, you study PP at Oxford, politics, philosophy, and economics, or you become a lawyer. So I think at the highest levels, you don't always have people with science knowledge, and I think that's a shame.
Yeah.
But I think on the whole, people are pretty accepting of science. I think a lot of people find it fascinating, but don't understand it. I mean, obviously, you've got books like Brief History of Time, apparently the most unread book in history. So,
I've read it. It's,
yeah, so
it's a fun book.
it is. Yeah.
I enjoyed it much better than Big Answers to Big Questions or Little Answers to Big Questions. Essentially his follow-up or his last book before he passed.
Oh, yes. Yeah. Yeah, I think I've read that one some time ago. Of course, the problem I have is that I know what he's talking about. So, it's, yeah, okay, he's going to do the no boundary proposal. Now he's going to do this, talk about black holes. I have actually studied all of this, so yeah, it's difficult to know how it's going to be received. In fact, what used to happen was that every Friday, the research group would have a dinner. Sorry, not a dinner, a lunchtime seminar. So it might be a student that's giving the seminar, or it might be an academic from some other place in the world. And Stephen would actually pay for the lunch. So a couple of the students would go out to the local supermarket and buy baguettes, pizzas, junk food, basically. And we'd all pile into one of the seminar rooms, and there was a microwave in the tea room, and that would be used to cook the pizzas, or actually probably not the microwave, perhaps it was nothing. I can't remember now. And so we'd have a lunch there, and it's all paid for by Stephen and his book royalties. So it's quite a nice thing.
Nice. So going back, so you don't think that science denialism is as large a problem as might seem to indicate within the YouTube
I think
community?
obviously, because we look at the flat Earth stuff, it sort of magnifies how much science denialism there is out there. So that's my impression. Anyway,
what I'm concerned, or what I'm worried about, is it does seem as if I realize that astronomy we refer to as a selection bias, and that I obviously I pay attention to science denialism on the internet, but it does seem like it's a growing problem. I don't know how large it is from a objective standpoint, but it does seem to be a growing problem, at least here in the States, particularly in terms of anti-vaxxers and COVID deniers and so forth and so on. I don't know if that you've encountered that, or if you have that opinion yourself over in the UK.
I haven't really noticed that. I mean, one thing we have in the UK is that pretty much all the political parties are on the same hymn sheet as when it comes to COVID. So you'll find that the Scottish government and the Welsh government, they're run by the SNP and the Scottish National Party and by Labour. And essentially, they're doing the same thing as the UK government is in terms of regulations. Okay, they slightly vary them. I think they vary them more to be different than for any other reason. But essentially, everyone's saying the same thing as far as COVID. So the people who are objecting seem to be a rather small minority. But yeah, and the figures I think seem to indicate that too. At least in the UK. I'm not sure about the States so much. I mean, but do you think this is anti-science, or is it more a distrust of experts?
Yes. Yeah, I think it's more of a distrust in experts than it is more of science denialism, as it were, because I think we see the same sorts of behaviors with, soft SIDS and, I hate using the term, but Karens, is that, there is a certain I hate to use the word entitlement, but this idea that um, they are smart enough to make their own decisions, and to hell with anyone who actually tells them any differently. So
Right.
yeah, I think there is a larger component of just not wanting to be told what to do, and being resentful for those folks who are in fact experts in their field of study.
Mm. Yeah.
I don't know. I don't know where that. I don't know where that. I'm interested in knowing where that comes from, because that does seem to be a larger, for me, it seems to be a growing problem.
What it sounds like, a lot of these people perhaps don't appreciate education and don't understand what it takes to get a good education, and how much effort and training you need to become an expert in something. I mean, I certainly noticed that with flat earthers. They think that they can just make up some random piece of non-physics and claim it's just as good as physics, which has been really painfully extracted from reality by some of the best minds over the last 2,000 years.
Yeah.
We've actually got, it's such a huge intellectual achievement to understand the universe in the way that it's understood today. And, these flat earthers and the like just seem to think that, they can just make up something silly about gravity or not, and think that's going to be just as good as what we've actually learned throughout our history. So, yeah.
What I'm kind of getting from my limited sort of, it's difficult to actually get flat earthers to actually talk about why they believe the things they believe, as opposed to what they believe. I could get Sleeping Warrior to talk about RDD until the cows come home. I mean,
Yeah.
In fact, I talked to him for 5 hours, but trying to understand exactly why they actually come up with it, I don't know. One of my hypotheses at this point is, I think that there is becoming this sort of undercurrent, or this belief that intelligence is people who are intelligent hold themselves above those who are, say, lesser intelligent. And I think there is a certain resentment among those folks that against the sort of these experts, as it were. I don't know. I'm not really phrasing that very, very well, I don't think. But do you feel that in our society that intelligence is praised in sort of evaluating someone's worth? Someone who is intelligent is inherently worth more than someone who is, shall we say, less intelligent?
I don't know about that. I think you could certainly make that that argument when you start looking at, say, celebrities coming from reality TV who seem to be lacking all sorts of intelligence, and you wonder how anyone could ever have anything to do with them, employ them, or anything at all, given their lack of intelligence and the way they behave.
Mm-hmm.
So perhaps there is something to that. I mean, one thing you do get is the portrayal of scientists and mathematicians in films. I've never liked the way scientists are portrayed as geeky or anything like or strange or socially awkward or any of those things.
Yeah.
I mean, some of them are, but some of them aren't as well, and it seems to be almost deliberate as a way to put scientists down,
pigeonhole them into a
So okay, this person's smart, but they have all these other flaws. So you can feel better about yourself because you may not be as smart as them, but at least you're not you don't have these other flaws.
Yeah.
So,
They're
and
not
you
as
see-
cool as everyone else.
Yeah.
Yeah, one of the things about this the series that I want to do was to sort of um, humanize scientists and let people know that we're pretty much just like everybody else. We just have a different interest in things.
Yeah.
But I don't know. One of the things I'm noticing is sort of contrary to that is you have what's the word I'm looking for? Popularization of or people. Elon Musk, Bill Gates, Steve Jobs. These are folks that are becoming more figures that are being more esteemed in our society. And, at least in the States, we
Right.
obviously has always been fandom of sports figures, but there does seem to be more of this fandom towards people who might be considered or had been considered nerds, as it were.
Yeah, I don't know about that. I'm not really a big fan of Elon Musk. I mean,
Neither
if
am
you've
I.
seen what Thunderfoot says about him, maybe I won't go quite that far. But
I might have to
uh,
check that out.
I think I think I certainly am in that direction with him. I mean, I'm not really a big fan of Bill Gates either. I think he does a lot of good work in terms of philanthropy, but
Mm-hmm.
I think Windows was a terrible idea, and I think you can look at the Microsoft business practices and the way that Microsoft actually turned the computer industry. I think it's held it back rather than promoted it due to their monopolistic and programming faults. So, yeah, I mean,
Yep.
I use Linux, and so does the department runs on Linux,
Yes.
and so on. So
When I was a student and doing research, I was also Linux. At the moment though, I've moved over to Microsoft because in a sense, Bill Gates was savvy enough to actually establish that, at least business wise, he was savvy enough to establish that monopoly. And I find for applications that I need to or that I would like to use for teaching, Windows is a much better option than say Linux. Um, I don't know if you hold to that opinion as well or not.
well, I'm not quite sure what you'd be referring to as far
So,
as
like for instance, just simple things like word processing. Uh,
later.
Yeah, you use LaTeX. At this point I use Word because LaTeX is. I don't know why I moved over away from LaTeX. Um, Mainly because I think it was mainly I think it's my own laziness. Word is far easier to use in my opinion than LaTeX is, although LaTeX is far more powerful. And I think that's really the a theme when in terms of Linux versus Windows is that Linux is a far more powerful operating system, whereas Windows is a far easier, user friendly, as it were, interface.
Right, yeah. I mean, I have very little experience of Windows. I sort of, well, Debian Linux was, well, there used to be a couple of people when I was doing a PhD who were computer scientists and were heavily involved in Debian Linux. I think two of them became head of the Debian Linux product. Head of the project of Debian Linux. So that was always the natural one to go for, and I think I changed over in spring of 1994. So I never saw Windows 95 or anything like that, and I went straight from Windows 3.1 to Linux, and thought Linux was a far better operating system at that time.
Yes.
It always was, and it always has been. So yeah.
Yeah, I just can't seem to find when you look at the sort of the power of Microsoft Office versus LibreOffice or Open Office at this point, I think it's called. Um,
Right.
I find Microsoft Office actually has a lot more options and it's just easier to put together presentations and things of that nature. And also when it comes to video editing software, I find there's a lot more options in terms of uh, on the Windows side than there is on the Linux side.
Okay, those aren't things that I do very often. I use for video editing. What do I use? I use a KDE program um, uh, for that, which it seems to work okay.
Yeah.
I've got a very old laptop. It's from 2007, and I've got a desktop from basically the same era. So the way my computer system works is I've got the desktop is connected to various external hard disks, and the NFS and my laptop NFS mounts those hard disks from via the desktop. So wherever I am, I've got loads of disk space, and it's very easy to do that under Linux. You know, it's basically invisible.
Yeah.
And also, my Google actually gave everyone in the university unlimited cloud storage. So
Must be nice.
Yeah, so I can mount my cloud storage as a directory, and I think it's 1.1 petabytes. So that's what it mounts at. But it seems to grow when I start uploading terabytes to it. It grows by that amount, so it does seem to be unlimited. Of course, the problem is that I don't really have bandwidth at home to make it very practical to put so much on there. But you see, what happened was that one of my external hard drives failed, and I'd always had lots of backup, and essentially one of the backup drives which failed. And then I thought to myself, well, Google are offering its external cloud storage.
Mm-hmm.
Let them worry about hard disk failures and backups. And I also found out that I could use a program called rclone, which had a way to encrypt any stuff I put on the cloud anyway. Okay. So my other worry putting stuff on the cloud was perhaps someone could hack into Google and then mess around with, look at all my files. And so because I was able to encrypt everything, it makes it easy to put loads of stuff there, back stuff up. So,
are you worried about just personal files being accessed, or is this more of a academic proprietary information that you're worried about?
Well, I mean, we have to be a little bit careful with some of the material that we're given, particularly when it comes to applications. So we wouldn't actually put those on the cloud. But no, I think it's more just keeping things, you might have stuff which is confidential, whether it be passwords, whether it be bank details or things like that. There's good reasons to keep stuff confidential, and if you can encrypt it and it doesn't really give an overhead, then why wouldn't you?
Yeah, so it's good, fairly good point. Yeah,
that's really it. So actually, part of the drive is encrypted, and part of it isn't. And it turns out that I can mount that Google Drive with the encrypted part on any machine. I don't have to have root access, so it makes it even easier to access files wherever I am. So I have been sort of moving all my backups to the cloud recently, and I can also stream from there. If I've got some videos there, I can. It's fast enough that you can still stream videos.
Yeah, pretty much everything that I do everything that all of my work is on the cloud. I use Dropbox as opposed to Google.
Yeah.
But I just find it far easier to be able to access, the same files from different machines. I don't have to worry about copying things over or bring around flash drives. If I have presentations or what have you, it's just all there. So, and it makes backing up things far easier.
Yeah.
I real quick, I do want to address something. I it's something in the chat where I use the term lesser intelligence, and that was I misspoke really on that. That's not really what I wanted to say. I just wanted to say folks with less aptitude in physics and in mathematics. I don't prescribe to.
Yeah.
I don't want to say that people who do not have an aptitude for physics or mathematics are of lesser intelligence. I realize that there are many different forms of intelligence. I just wanted to clarify that's not what I meant. For if anyone in the audience or future people who watch take umbrage to that.
I guess that's fair enough. But of course, we know what you really mean.
Yeah. So I just wanted to put that out there. But so just kind of wrapping this up because we're approaching around the 2.5 hour mark. I wanted to ask you just a couple of questions. Of one of the questions I want to ask is Star Wars versus Star Trek.
Star Wars. I mean, I did see. I guess I saw Space Track, the original series, when I was a kid. But and I saw all the films with the original cast, and perhaps one or two of the films with the with I was going to say the new guy. He's probably not the new guy anymore. Patrick Stewart.
Oh
so
yeah,
I saw one or two of those, but I haven't watched any other ones. Perhaps you're a Trekkie, aren't you?
At this point, I'm so frustrated with both franchises that I don't know. I don't know really the answer to that question. But yeah, in the past, I've been much more Star Trek than I have been with Star Wars. I find that Star Trek has because it's more science fiction as opposed to science fantasy. I feel that Star Trek has a larger ability to address contemporary issues or social issues, challenge our ideas of what is possible and how our society works than it does with Star Wars. But
right.
So you were saying my memory is Swiss cheese, but you're saying Star Wars. That's
I did enjoy Star Wars when it first came out and the original trilogy. Wasn't a great fan of the Phantom Menace or the I did quite like Revenge of the Sith, except I was a bit bored with the fight at the end. It just went on too long.
Yes,
but I can understand why they needed to make it a big event, though. Then what was the episode 7? It's
The Force Awakens.
The Force Awakens, yes. That was instantly forgettable, I think. It's a rehash of the original one as well. And then there was
Last Jedi.
No, we don't talk about that. Then was the final one.
Rise of Skywalker. Yeah.
I didn't mind that too much. I think they were trying to undo what had been done in the previous one. I mean, it wasn't great, but at least Palpatine's back, who I think is a hero throughout the entire series. I hear that might be another one.
So you like the idea that they brought Palpatine back?
Well, I was always a fan of Palpatine. He's a hero. So I was glad that he was back. Unfortunately, they killed him off at the end.
Well, they supposedly killed him off at the end of Jedi as well. So who knows?
Yeah.
They'll go back to that well. So what was your? So I actually never watched. I have not actually watched Rise of Skywalker because of so many people that I've friends of mine whose opinion I trust. They hated it. They absolutely could not stand Rise of Skywalker. They basically just said it was a whole bunch of fan service and the story didn't make any sense. But I'm curious
Well,
why. What is your problem with Last Jedi, which I didn't like either. But uh, I'm curious on which side of the sort of the discussion when it comes to that one you're on.
oh, I'm not quite sure why I didn't like it that much. I just didn't like the story. Just didn't seem to be very interesting. Uh,
Because the two minds that I've talked to, people seem to. It's a very polarizing film. People either seem to love it or they hate it based on the fact that Ryan Johnson was trying to subvert expectations and do things that we've never really seen in a Star Wars movie before.
well,
So,
perhaps making it so different what was the problem.
hmm,
I just thought it was okay. I could put up with episode 7, but episode 8, it was just sort of, do I really want to watch this? I mean, I don't have a real high tolerance for films anyway, because I don't watch many films at all.
mhm.
And usually I often get bored with films and turn them off before the end. So, yeah, that was one I only stuck with because it was a Star Wars film. And I was always a Star Wars fan. But yeah, uh, yeah, the sequels have not been good.
No.
Although
So,
I,
go ahead.
I think The Mandalorian and the Book of Boba Fett seem much better, and they are from Disney as well. So it's not just the Disney connection which made those films bad. But
No, I don't think it's. I don't. Well, what I blame Disney for is, which is surprising because they also own Marvel, or at least they own the Marvel Studios. Is that with Marvel Studios there seems to be uh, at least coherency in the storyline. They from one film to another there is a lot of connecting tissue that makes sense.
yeah,
And I thought they were going to bring that sort of mentality to the next three or these 7, 8, 9, but they
yeah,
didn't. And I think that was where it basically fell apart. Is that you had J.J. Abrams who had a vision of what this trilogy was going to be about. You had Ryan Johnson who decided,
yeah,
no, I am not going to follow through with any of that. I have my own vision. And then when they brought, I think it was, I can't remember who they originally tapped to do the third one, but when he fell through over creative differences, they brought J.J. Abrams back, and he basically just, as you say, erased everything from
yeah.
the Last Jedi. So I think Disney, in a sense, failed. That was their major problem, is that they failed to actually have a cohesive story over all three movies.
Yeah, but I think basically the sequel stories were never going to be as good as the original trilogy.
Hmm,
And yeah.
true. So if you're not into film, what is sort of your pastime? Do you enjoy reading, or um, so I
Uh,
guess what are your hobbies as well?
I do a lot of mathematics. I'm writing this book if I do have any spare time and I'm not watching um, idiots on the internet say that. Uh, yeah, I don't have much time for other things. I mean, I have been watching quite a lot of the Grand Tour and Top Gear recently.
Oh,
But,
nice.
I always like that stuff. But,
Okay.
yeah, and I'm a big sport fan as well. So
Oh.
I was I was up till 8 a.m. this morning following the cricket. So, England
I
was
have to admit,
relatively.
I don't understand the appeal of cricket at all. Although I also don't understand cricket at all. So that might be there might be a correlation there.
Yeah, yeah. I mean, the thing with cricket is you sort of intend to put it on in the background, and yeah, it's going to go on all day. But unfortunately, it does draw you in a
Okay.
bit, and so it does take a long time. Uh, I mean, I don't, I have not really played cricket. We didn't really play it at school or anything like that. Um, I did play football and rugby for my college, So
Okay,
I think you said in the past you like rugby.
I do.
So
I do.
yeah,
I
yeah,
don't get a lot of exposure to it over here, but I do. What little I've seen, I do enjoy quite a bit. I think
yeah.
I enjoy it much better than American football. In
Right. Yeah.
actuality,
Why is that?
um, so it's I I enjoy American football more than I enjoy European football or football, as it were.
Right.
Um, and I like rugby basically because the main I agree that the main problem that I've heard from football fans of American football is that it's somewhat boring to watch because it starts and stops. I mean, you have a play, you stop, basically reset, you play again. That really doesn't bother me so much. I still enjoy
Yeah.
the overall action of the sport, but rugby seems to give me that and also get rid of that basically stoppage of play. It's much more of an active
Yeah.
going sport.
One thing I also think is that because the play in American football always starts in the middle of the pitch, it's sort of more of a one-dimensional thing where you're trying to make your way up the pitch or the field, whatever you call it.
Yeah,
Whereas in rugby, the play takes place in all parts of the field, so it's more of a two-dimensional game as opposed to a one-dimensional game. Uh,
true.
so
Yeah, I hadn't really thought of it that way. I guess in the same way, that's really why I appreciate hockey.
right,
Is it's much more a fast paced game, and as you say, it's a much more dimension. It has a lot more dimensionality to it. Well, two
mm,
dimensions rather, because the play can go all over the place.
yeah.
So, all right,
I
well,
mean,
yeah, go
the
ahead.
other thing I did actually do as a student was row, because I think when you're in Cambridge, you should do a little bit of rowing.
Is that sort of an obligation of being at Cambridge?
Yeah. Although actually, you do get uh, outings at silly times in the morning because you have to do it before lectures, and so you'll be up at 5 a.m. to go down to the water, which is ice cold, in part of town, and take the boat out and so on. So I did give it up in the end when I started dreaming about rowing. So
When you started noticing it was sort of taking over your entire life.
yeah, I mean, it's. I'm glad I did it for the experience, but yeah, it does take up a lot of time, and yeah, the early mornings were never good for me. Um, in the Easter term, you could do it in the late evenings, but that was rare. But,
Why do you have to do it in the early morning? I've always wondered why was rowing always an early morning or late evening? Is it just because it's less congested?
well, you need to get 8 people together, and you need to um, it needs to be at a time when um, they don't have other obligations with their work. So that tends to mean that well, afternoons are taken up with things like supervision and the like. So it will be dark if you go anytime after lectures are finished. Well, sort of after your day is finished, if you try and go out in the evenings, it's pitch black, so you can't do it then. So the only time you have is very early mornings, and
So
everyone's
it's more of a
back.
scheduling issue than anything else.
Yeah, and so yeah, unless you're everyone has to be back and showered and then off to lectures at 9 o'clock. So it has to be extremely early in the morning.
Hmm,
Uh,
makes sense.
particularly when you've got to take the boat out yourself and then put it back and cycle to and from college. So yeah, in the summer it's not too bad, but of course people have exams. So again, it's you probably only do it perhaps after exams, and then you have long evenings where you can do an outing.
Okay.
So,
So it's
okay.
sort of we're talking about with the sort of stereotype of the geeky, socially awkward scientist. Were you athletically inclined as growing up, or was that something you got into in college?
Yeah, I was always quite athletic. Um, I was I was rarely ever the very best at anything athletic, but I was usually sort of the second string down. So yeah, yeah, I always enjoyed sports, and particularly football, and to some extent rugby. We didn't play that much rugby at school. Uh, uh, I think at school we had the choice in our third year: do we want to play, uh, have our games lessons as rugby lessons or football lessons? And I wouldn't have minded either, but
Hmm.
I think the majority wanted it to be football, so uh, football it was. Uh, but, yeah,
Is there
yeah,
a large culture of athleticism at Cambridge? I mean, is this something that a lot of
yeah.
students participate in?
Yes, because we have so many colleges, there's a lot of inter-college sport that goes on. And with each
Makes
college
sense.
having, say, 600 students, then there's a good chance if you're interested in playing rugby that you'll be in a team which can play against other colleges, and and you'd be able to compete at all levels. So perhaps, and also the thing is, all the colleges generally have sports grounds, and some of the colleges have sports grounds actually on site. So Churchill, for instance, one of the things which attracted me to that college was that they had the sports grounds actually on the site. So yeah, there's a big sporting community uh, or opportunities in Cambridge.
Interesting. Yeah, there's really when it comes to sports, at least again, my experience is larger state universities here in the states. Um, there are intramural sports, but they're not nearly as popular as it seems like they would be at Cambridge. There is for sports in the states, it's really at the highest levels where
Right.
you actually go you pretty much are going to college to participate in said sport as opposed
Right.
to primarily concentrating on your education.
Yeah.
Um,
Well, my dad went to Loughborough University, which is really the sports university in the UK. He actually left after a year, but I think during that time he took part in certain university teams. So he was very much into his sport. Uh, so
okay. Well, I hate to end this
okay,
conversation, but it's getting we're approaching the 2 hour 40 minute mark, and so and I have a telescope that desperately
okay,
needs my attention. Yeah, we had it was weird. We had a glitch which caused our telescope to start tracking. It came on and the telescope started tracking, and no one was there or monitoring it, so it decided to flip all the way around, which
you've got
telescopes
ghosts.
pointing at the ground is a bad idea.
I reckon it's ghosts or UFOs or something. It's aliens trying to get in contact, and this is how they've decided to do it.
that that would be. I'll have to look into that.
Right.
All right.
Okay.
All right, Clive. I'm gonna. All right,
Okay.
folks. I'm gonna roll the outro here in a second. But thank you all. Thank you everyone for stopping by and listening to Clive and I have a chat. Uh, I I didn't want to interrupt our conversation. A shout out to people, but I see blue marbles in the chat. Eddie Tusk managed to make it. Carl Edwards. Thank you all again, Ardo. I don't think I've ever seen Ardo in my chat before, so I'm glad that they made it. Hi, Demon Orb, Professor Phil Bell. But again, thank you all for being with us and listening to us talk about science and academia and so forth. I don't at the moment have a speaker lined up for next week or for next Sunday. I'm hoping to get Maddie from Science Side Up. I'm going to be contacting her later today to get that. Um, Clive, do you have any last words that you'd like to mention?
Only thanks for having me on. It's been a pleasure, and thanks to the chat. Unfortunately, I wasn't able to read what was going on. It's a bit too distracting when you're trying to talk or answer questions. But yeah, it's been a pleasure.
Oh, appreciate that. Yes, thank you. Yeah, it's definitely been an honor having you on the stream. So, all right, folks, peace out, and I will see you next time.